friends, Mrs. McBride here, coming to you straight from my kitchen table. Second video of the day, so you know what that means. Second joke. Where do fish get their money? From the loan shark. All right, now a couple of things. This I find can be a little bit tricky, so make sure you follow along. I'm gonna do the example here on page 13 in your notes, and then I'm also gonna do another example, which if you had a separate sheet of paper ready to go for that one, that would be great. You'll need your calculator, and you may wanna write some stuff on your green sheet today, so just a little heads up. Okay, so here we go. Now we're going to put it all together, and as you can see here, we've got a circuit that has resistors that are both in series and parallel, and it looks kind of like a mess. Now, lucky for you that I have come up with 5 steps that we're going to use for every one of these problems that we solve. So the first thing we're going to do is find REQ. The second thing we'll do is we'll find total current. The third thing, we'll ask ourselves, which, if any, resistor gets the total current? Then we're going to divide the current. This is the most difficult step here. This is where we're going to make our money, okay? This is what's going to be tricky, but I know you guys can do it, okay? And then we're going to VERP it. So step 5 is probably the easiest one. Once we can do step 4, we're in business. Okay, so the first thing we're going to do is find REQ. Now, what I would recommend doing is, if you like these steps, go ahead and write these on your green sheet. If you're not feeling it or you think that you don't need them, then don't, okay? So I'm just going to use this piece of paper, that way we can keep going back and forth. All right, so the first thing we need to do is find REQ. The way that we do this is we're going to ask ourselves, just the same way we did this in the last video, is do we have any resistors that are just in series or just in parallel right now? Okay, hopefully you are saying to yourself, yes we do, it is these, okay? And again, as a reminder, these two are not just in parallel because this one sort of is in the way. When we take our fingers and we trace down, the 6.2 is in the way, okay? So let's go ahead and redraw this. Where am I gonna redraw this? Let me redraw this down here. Okay, so I'm gonna redraw that this here, that's my battery. This is my 11. This is my 7.5, and I'm going to redraw that like this. Okay, so these two are in series, so since they're in series, we can just go ahead and add them together. Okay, so when we add these together, we should get 18.2. All right, the next thing you're saying to yourself is, do I see any resistors that are just in series or just in parallel? Okay, aha. These two are in parallel, okay? I'm gonna jump the gun here and redraw. What will this look like when I do this? So this will be the 11, okay? So I've got 2 resistors that are in parallel. Remember, when I have resistors that are in parallel, I have to do 1 divided by 7.5 plus 1 divided by 18.2. Okay, and again, this right here is not the answer. We need to do 1 divided by this to get the answer. All right, I'm going to call that 5.3. So this is 5.3. Okay, so we would find REQ by taking and adding these together. I'm just going to write this down. I think this is a good step here. And saying that 11 plus 5.3 gives me a value of 16.3 ohms. Okay? Now you notice that doesn't really go in the table, but that's okay. All right, so step number 1, check. Step number 2 says find the total current. Okay? Will do. So we can use the equation VT equals IT times REQ to find the total current. Now the total voltage is the voltage given by the battery. So this one is 15. I don't know what IT is, and I want to find, I found REQ. Okay, so I should be able to find what IT is by dividing 15 by 16.3, okay? So this gives me IT is equal to 15 divided by 16.3, or let's call this 0.92. Okay, I'm gonna box this because I can. All right, there we go. All right, back to my problem solving steps. Step number 2, found IT. Step number 3 says which, if any, gets the total current, okay? So which, if any, of these resistors gets the total current? Okay, what do you think? Which one of these, if any of them, get the total current? For me, I would say there's only one resistor that gets the total current, and that one would be the 11. The current gets divided through all the rest of them, but the 11 gets the full dose. So I'm gonna go ahead and put 0.92 in here. And while I'm at it, I'm just gonna go ahead and fill in the resistor values here. Okay, now I told you this was gonna be the toughest part here, all right? This next part. So I'm gonna look at this picture here. Because these two resistors are in series, and we know that resistors in series are going to get the same amount of current. So whatever this resistor gets, this one gets the same thing, right? So these two resistors, these two boxes should be the same. Okay, so I can almost pretend that it looks like this picture here. Okay, now how do I figure out what proportion each resistor gets? Well, I divide the current. So I start by doing, for each one of these, I'm going to do part over whole times IT. Okay, so let's first figure out the whole. What is 7.5 plus 18.2? It's late, and I don't know off the top of my head. I'm sure you were all yelling at me. It is 25.7. Okay. So one of these is 7.5 over 25.7 times my total current, which is 0.92. The other one is 18.2 over my whole times 0.92. Okay, so you see how we had to do that twice because we had two different pieces, right? Some current goes down here and some goes down here. And again, the reason that we could add these together is because they're in series and they get the same current. Okay, so let's do some math here. Let's do 7.5 divided by 25.7 times 0.92. Okay, let's call that, we'll round up and call that 0.27. Okay, and then we'll do the same thing here. We'll do 18.2 divided by 25.7 times 0.92. Okay, let's round that and call this 0.65. Okay, now you might be saying to yourself, we're done. One more thing. Do you remember how I told you that current takes the path of least resistance? That the smaller the resistor value, the larger the current. Well, right now, that doesn't really match. Right now, the larger value has the larger current, and the smaller value has the smaller current. So here's what we have to do. We have to flip-flop these, okay? So what does this mean when I'm going and plugging this into my table, okay? So the 6.2 and the 12, we said these are both going to get the same current. And they're going to get a current of 0.27. Okay, and the 7.5, what is its current? Well, it's going to have a current of 0.65. Okay, so we've now officially divided the current. Now verbing it is easy, right? Because we should be able to use two of our very good friends. We should be able to use V equals IR and P equals IV, okay? So let's do the first one together, and then I will ask you to pause the video and you can go ahead and do the rest on your own. So if we do this one here, if we take current times resistance, that's our 0.92 times 11. 0.92 times 11. 10.12. Okay, and then to find the power, we do power equals current times voltage. Okay, so this is going to be our 10.12 times 0.92. Okay, and I'm going to get 9.3. Okay, please pause the video and go ahead and do the rest. Okay, hope you got all the right answers. Now, if you're saying to yourself, I am not feeling good about this, I got another problem for you. If you're saying to yourself, I am feeling good about this, then go ahead and stop the video and try the practice. Okay, so I'm just taking out a blank piece of paper and I'm going to give you another problem. Okay, let's say that this is 3 ohms, 6 ohms, 3 ohms, and 9 volts. How come nobody said it wasn't in view? All right, take 2. How's that look? Pause if you need to. That's why I already have these pre-printed. V, I, R, P, R1, R2, R3. Let's say that this one goes with this 3 and 6 and 3. Okay, you ready? You ready for business here? All right. First order of business, find REQ. Do you see any resistors that are only in series or only in parallel? Hopefully you are saying, yes, these are in parallel. So if I'm going to redraw, this was the 3. Okay, and since they're in parallel, I'm going to do 1 over 6 plus 1 over 3. You're right, we have to do 1 over that. And we get an answer of 2. Okay, this works out nicely because REQ is going to give us a nice, beautiful number. All right, because these two are in series, and if they're in series, that means we can add them, or that means that our REQ is 5 ohms. Okay, step 1, down. Step 2, find IT. Okay, we can use our VT equals IT times REQ. Total voltage, 9. Total current, I don't know. REQ, 5. Okay, so if we take and we solve for IT, you should get that IT equals 1.8 amps. All right, step 2, done. Step 3, which, if any, gets the total current? Which resistor, if any of these, gets the total current? Where does all the current travel through? Hopefully you're saying this first 3 ohm resistor. Okay? Now, once we do that, everybody's favorite step of dividing the current. So here we go. Let's divide. These are the ones that we have left. So again, remember, we're doing part over whole times IT. Right? So what is the whole in this case? The whole is 9, right? So we're going to do 6/9 of our total current, and then 3/9 of our total current. Okay? 6/9 of 1.8 is 1.2. And 3/9 of 1.8 is 0.6. Are we good to go? Does the 6 get 1.2? Nope, because remember, current always takes the path of least resistance. The larger value goes with the smaller number, and the smaller goes with the larger. Remember, current is lazy. Most of the current will take the path of the least resistance. Okay, so 6 gets the 0.6, and 3 gets the 1.2. Okay, once we've divided the current, then it's super easy. We should be able to just VERP it using our V equals IR and P equals IV. Okay, please go ahead and pause the video and VERP it. For those of you who are ready, here are the answers. Okay, now you might be saying to yourself, that's kind of weird that these two have the same voltage, right? No, it's not, because remember, these two are in parallel. And what do we know about resistors that are in parallel? We know that resistors that are in parallel have the same voltage. So this to me tells me, yes, we did it. We were correct. All right, bye friends, talk to you soon.